Okay, I think we are actually live on YouTube and perhaps a little prematurely, a few seconds earlier than usual. So maybe I'll just give it a couple of minutes, or maybe not a couple of minutes, just a few moments till we have some of the other folks join in, and then we'll get started. Just a reminder that this is our final meetup for now. And hopefully, hopefully we'll get back in January or something like this to get some closure on the remaining 5 miniatures that we didn't get around to doing in this particular run of discussions. So okay, hey, hi Manan, good evening. Yes, all right. So okay, probably a good time as any to get started. So as I hinted at yesterday, we're going to be skipping ahead a little bit and skipping past a couple of graph theory themed miniatures onto equilateral sets. And these are sets which these are collections of points that are basically mutually equidistant. And this might ring the bell because I think way back in, I think, miniature number 15 or so, we talked about only two distances. So back then we said, well, um, what if you want to maximize a collection of points which have the property that if you made a list of all the pairwise distances, you only see two distinct things on that list. And even when we were discussing this back then, we did figure that a more preliminary question would be, well, what if you were only allowed to see one distance? Then how large could your list be? And it turns out that I think we saw that if you're an RD and you're talking about Euclidean distance, then this is capped off at d plus 1 points. So for instance, in R2, you can have 3 points that are mutually equidistant. So you have the triangle, but you have the equilateral triangle, but you cannot push your luck beyond this. For instance, if you go to a square, then the consecutive points in the boundary all are one apart, say if it's a unit square, but the diagonals do manifest a different distance. So that would be a nice example for two distances where it's no longer one distance anymore. And you can do a pretty, like by now, what we could think of as a standard dimensionality based argument for showing that d plus 1 is actually the best that you can hope for in RD for as long as you're working with the Euclidean distance. So the reason I'm emphasizing that we're working with the Euclidean distance explicitly is because in this particular miniature, we're going to look at the Euclidean distance, briefly look at the L infinity distance, and a lot of the focus will actually be on the L1 distance. So we're going beyond the sort of default distance concept that we've been used to so far. So that's why the qualifiers. But before we get into L infinity and L1 distances, we want to talk about a relaxation, a different kind of relaxation of the equidistant notion. So previously we said, well, instead of insisting that all your points are pairwise exactly the same distance apart, we allow you to see two distances, but a smoother notion of saying that you're close to being equidistant is to allow ourselves to be, approximately the same distance. So remember that when we said only two distances, those two distances could be potentially very different from each other. Although I suppose geometrically, maybe it's not tenable to be in a situation where one distance is ultra small and the other is ultra large. Who knows? Maybe it's possible. But anyway, the point is that those two distances have nothing to do with each other. Whereas here, when we talk about approximately equilateral sets, what we are saying is, well, you have a bunch of points that are well, here, this is not quite the Euclidean distance, but the square Euclidean distance that we are talking about. So for every pair of points, their distance is within 1 plus minus root n window of 1. So they're almost unit apart in some sense. There's a very tiny error that we're allowing for. So if you were like, if you're looking at this point set with your naked eye, it probably feels like a equidistant point set. That's kind of the idea. Whereas with only two distances, it's visibly going to be, in many situations, not quote unquote close to being equidistant. Okay, so it's this concept of so this is of course stated as a proposition here, but what we see here, if you have points that satisfy this property, we call them approximately equilateral. You could do a plus minus epsilon perhaps and parameterize the notion by epsilon, but here for some reason we are fixated on epsilon being specifically 1 over root n. But is this definition of approximately an approximately equilateral set of points in RD, is the definition okay? Give me a +1 if it makes sense. Okay, super. So the claim, of course, is that, well, even with this relaxed notion, you can't have arbitrarily large sets. Is still kind of constrained. So previously, with strictly equilateral sets, we had a bound of d plus 1. And now it's a slightly, well, the ceiling has gone up. It's now 2 times d plus 2. And now I can't remember if the miniature talks about this. I suppose you could ask if there are point sets that achieve this bound. I don't know if somebody wants to think about that in parallel. I don't remember if the miniature had an example, and I don't remember if I thought about it very much because I was it's mostly focused on trying to figure out what's going on with the proof. But okay, so that's a valid question to think about. Is there a point set that achieves? Is there an approximately equilateral point set that achieves this bound? And it may be worth thinking about, just say, I don't know, d equals 2 or something. That becomes what we want: a collection of 8 points, which are all within 1 plus minus 1 over square root 2 apart. Sorry, not square root 2, but square root of 8. So yeah, because n is, we want to see if this bound is actually tight. So if d is 2, then you're saying that n is at most 2 times 4 or 8. So then this bound in turn is going to be 1 plus minus 1 plus minus 1 over square root of 8. So 2 root 2 or something like that. It's no easier to write. So yeah, that's a concrete question. Can we come up with a collection of 8 points which are practically unit distance apart? The margin of error is 1 over square root of 8. So if you like your whatever geometry puzzles, here is one to think about. Okay, all right. But that's not something that I'm going to spend any more time on right now. But like I said, we're happy to circle back to it if anybody has suggestions. But for now, let's try to come up with a proof of the upper bound. Let's try to discuss a proof of the upper bound. For this, we are going to again rely on some linear algebra, and I'm going to again, so once again, in the interest of time, there are like a couple of technical lemmas here that I'm going to kind of take as a given. However, this particular one, the first one that I'm going to take as a given, the so-called rank lemma, says that if you have a real symmetric n by n matrix, which is non-zero, then the rank is lower bounded by this expression that you see on the right. And like I said, I don't expect to have time to prove this, so I was even lazy and didn't even try putting up a proof on the slides. But it turns out that, if you replace the entries here with okay, so maybe this is not a very clever way of saying it, but okay, so essentially the idea is to leverage the fact that if you have a real symmetric n by n matrix, then the matrix is going to have n eigenvalues at most, and these eigenvalues are going to be real. So you can basically mess around with these eigenvalues, some of which may potentially be 0, but it turns out you don't really care. But take your n eigenvalues and apply the Cauchy-Schwarz inequality on the eigenvalues to get something that looks a whole lot like this. And then you kind of use the fact that the eigenvalues are closely related to the trace, and the eigenvalues of a squared or lambda squared, things like that. So a lot of cute little facts come together to give you a proof of this lemma. So, I mean, it's very doable. And now I'm probably, as I speak, feeling a little bad that I didn't actually write it out. But yeah, I mean, it's not. It's not a technical lemma that's awkward to work with. It's basically using the connection between the entries of the matrix and the eigenvalues, a little bit of Cauchy-Schwarz and just clever substitutions. So that's something that I'm going to not get into. It's very unlikely even that we have time left at the end and we feel like we want to get into it, that I can probably try to cobble something together. But for now, let's take this as something that we believe. But from here, I want a consequence, which is that if we have the identity matrix with once, so we have the identity matrix perturbed slightly, by which I mean that we have ones on the diagonal, just as we do in IN. All the off-diagonal entries in magnitude are at most 1 over root n. Then by just, again, substitution, we get that rank of A is at least n by 2. So basically, something that's close to IN still has large rank is what we get out of this. So this is, so this is just, it is really an immediate consequence of the previous rank lemma, which gives us this bound that you see on top. And if you were to just plug in the values from the matrix A in the corollary, then notice that when you sum AII, you get n, right? Because you have ones in the diagonals. And in the denominator, what's going on? We are summing the squares of all the individual entries. So the squares of the diagonal entries is still going to be 1 squared is 1. So you sum those, there are n of those. So that sum turns out to be n. All the off-diagonal entries, when you square them, their values are going to be at most 1 over n. And there are n squared minus n of these off-diagonal entries. So you're going to add another 1 over n times n squared minus n to the mix on top of n. That's the denominator. So I shouldn't have said that this is equal, because these entries are the off-diagonal entries. We only have a bound, but because it's in the denominator, it's okay for me to substitute with something that's an upper bound, because that only makes this quantity smaller, and we are proving, it makes the denominator smaller, and the overall quantity, I mean, hopefully the inequality does work out in the right direction. Let me just make sure that I didn't take a leap of faith here. So each of the off-diagonal entries are bounded by 1 over root n. So this expression here is a valid upper bound, right? So this guy is going to be less than or equal to, this sum here is going to be less than or equal to what we have written there, but these fellows are in the denominator. So this inequality moves in the right direction. So hopefully we are good. Now that's, well, you have that n that's going to cancel out. So you basically have n squared over 2n minus 1, again, substituting for, well, it's just doing 2n instead of 2n minus 1, safe to do, because we again in the denominator, we get n over 2. Okay, so this is just, this is just substitution in the previous expression, but this is the form of the rank lemma that we are going to actually use. So I figured this was worth stating explicitly. So does the corollary make sense? So we have a lower bound on the rank of the identity matrix with the entries with the off-diagonal entries being within a plus minus 1 over root n magnitude. Give me a +1 if the statement of the corollary is fine, and then we will try to see how we can plug this in to get a proof of the proposition on the screen. Okay, super, thank you. So we will then proceed by considering this n by n matrix where Aij is defined to be 1 minus the distance between Pi and Pj's, the square of the Euclidean distance between the ith and the jth point. So this distance here, because it's an approximately equilateral set, we know that the square distance between the ith and the jth point in our set is within, it's within a small, it's within one over root n of 1. We know that that's what this is. And now we have knocked out 1 from it. So the Aij entries are therefore in magnitude at most 1 over root n, just like in the premise of the corollary. So we're going to be able to apply our corollary to this matrix A that we have just defined to see that this has rank at least n by 2. And as we have done a few times in previous miniatures, we now have this lower bound on the rank. So if we can combine it with an upper bound, which looks like this, so if we can say that the rank is at most d by 2, we know that it is at least n by 2, but if we can say that it's at most d by 2, then we get what we want, right? So you can forget about the rank in the middle. You'll see that n is at most 2 times d by 2. So if we can show this part, if we can show the first inequality, then we are in business. And for this, again, we're going to use ideas that probably look similar, but we're going to write out A in terms of some functions and show that those functions can be expressed using a small set of core functions. We just think of them as a basis that'll end up bounding the rank of A. So let's take a look. So I'm going to define a collection, a family of n functions. This basically is designed to describe the ith row of the matrix A. So Fi basically, okay, so this is Fi. Fi takes, notice that if you plug in some Pj into Fi, then the expression that you get is exactly the Aij entry, right? Because, yeah, this is, Aj entry, I suppose. So, so if I plug in Pj into Fi, then I get 1 minus Pj minus Pi squared. So essentially think of the ith row of the matrix A as being Fi acting on all of these points. Yeah, so that's you could think of it as a convenient way of rewriting the entries of the matrix. Let me know if this reformulation makes sense, if the function Fi makes sense, right? So Fi takes a point in Rd as input, so it's dealing with a vector in Rd, and it maps it to a point in R, which is basically the distance between the square distance between Pi and Pj, but adjusted for this one with a 1 minus, because we want to take advantage of this rank lower bound that we have, right? So let me know if the definition of Fi is okay. Okay, all right, great. So, oops. Okay, so this was Fi, and you can just expand Fi out to see that this is what it looks like. Now, I don't remember exactly which miniature this was. Was it, again, only 2 distances? There was a miniature where, if you remember, we wrote out a bunch of functions, and we said that, well, all of these functions, which I think back then were polynomials, we said that we can express this as linear combinations of a small set of functions. So you remember we had some monomials, and we first said that, well, okay, all of these can be described by at most so many monomials, but then we took a closer look at the functions and said that they can be written as a linear combination of a much smaller set of functions, and that's what gave us the bound that we wanted. So this is kind of in a similar spirit. So Fi can be written as, well, this is just expanding out this square term here. And I don't know, is it visibly clear that Fi can be expressed as a linear combination of a small set of functions? So we have that there is a constant term in Fi. We have that we have this squaring business going on. And then we have, I suppose this could also be thought of as, then we have these terms, which are basically, in some sense, you're pulling out the individual coordinates, right? So if I had a function which pulled out just the second coordinate, I had a function which pulled out just the first coordinate, those could be basic ingredients for me to write out the function Fi. But I need probably not just the coordinate pulling, I probably need a little bit more as well. So if I were to ask you, like, can all the Fi's be expressed as a linear combination of a small set of core functions? Could you think about maybe how many? Probably there's a little bit of reverse engineering from what we have set out to prove, but even otherwise, by just maybe staring at the form of the function Fi, can we say something?
You have marked exactly D plus 2 of them, no?
I have marked D plus 2 things, yes. And I don't know if it's, I don't know if that's a bit of a giveaway, yes. So indeed, basically one function that gives me the squaring effect, one function that, pulls out the ith coordinate, and one function that can give me the additive constant. These are all ingredients that are enough for me to express any of the Fi's. So there are D plus 2 the D plus. So notice that Fi, well, there are n of the Fi's, but they can all be expressed as linear combinations of D plus 2 things: the constant function, the squaring function, and the individual coordinate functions. So this is a list of D plus 2 functions. And if you think about the vector space that's generated by these D plus 2 functions, that has, well, because this is a generating set, that has dimension D plus 2. And all of my Fi's are sitting in that space, right? So the collection of the Fi's, the n of them, but in terms of dimension, the dimension of all of these Fi's is really, D plus 2. So you can think of this as indirectly bounding also the rank of A, because these Fi's express the entries of A. So this is, again, I guess I'm not opening this up much more because it's a technique. This is something that we have seen before, but let me know if anything about the approach or anything about how we are bounding the space of the dimension of the space of the Fi's, the space that the Fi's are sitting in. If any of that seems fishy, let me know. But otherwise, also maybe let me know if you're convinced about the proposition, and everything falls in place once you have this part of the inequality, which is this upper bound and the rank of A. So the upper and the lower bound conspire together to give you what you want. So give me a +1 if this kind of makes sense. And then we can move on to the weirder distances, the L infinity and the L1 distances. That's what's coming up next. And we'll see, basically the goal from here is to say that, okay, can we use this proposition, which is a fact about approximately equilateral sets with respect to the Euclidean distance, to meaningfully reason about other kinds of distances. So again, there's going to be some sort of transportation between L1 distances and Euclidean distances. So we are going to use this proposition in the sort of the second half of the story. So give me a +1 if we can move on, or let me know if you have questions. Okay, sounds good. Thanks for the sort of the go ahead. Okay, so let's recall that we were thinking about equilateral sets, and let's look at, well, just as a warm-up, let's look at the L infinity distance, which basically is the largest difference between any pair of coordinates. Like, you go over all the coordinates, and what you want is to pick out the largest difference. And it turns out that the L infinity distance, I'll state this without proof, that you can have exponentially many points as opposed to all the linear bounds we've seen with the Euclidean distances. With the L infinity distance, you can have as many as 2 to the d points in RD, which are quote unquote equilateral. I don't have a proof for the fact that you cannot do better than this, but is maybe we can come up with an example. So can we come up with an example of 2 to the d points which actually have this property? And there's actually a natural, well, I mean, one place to start would be to work with the standard basis. And then 2 to the d as a number should probably already be suggestive of something. So in d, when d is equal to 2, this is 2 squared is 4. You're probably automatically thinking of a square. In R3, 2 cubed is 8. You're probably thinking about the corners of some sort of a cube. So does anybody want to pick up on this and suggest an example of a collection of 2 to the d points which are equidistant under the L infinity distance? The 2 to the d is also the number of subsets of 1 to d, and we have d coordinates. So yeah, so I may have just spoiled it a little too much, but yeah, if anybody wants to make this explicit, that would be great. Yeah, exactly. Your binary choice for each dimension. Exactly. So for each of the coordinates, decide if you want a 1 or 0. So these are all your vectors. So thank you, Sat. That's perfect. So these are also the corners of the Boolean hypercube in d dimensions. Yeah, that would, I think, not be wrong to say that. And so you have 2 to the d of those. And are they equilateral in the sense that because well, the coordinates are all 0s and 1s. So when they collide, they're either going to vanish. I mean, the difference will either be a 1 minus 1 or a 0 minus 0, in which case that's 0. But notice that as long as you're looking at 2 distinct vectors, there's going to be at least one coordinate where one of the vectors reports a 1 and the other guy reports a 0. So that absolute difference is going to be 1. And you cannot see any other kind of difference. So all the coordinate-wise differences are going to be either 0 or 1. So the max is always going to turn out to be a 1. So there is the sense in which this is an equilateral set under the L infinity norm. Yeah. So everyone convinced with this example? You can push your luck and go up to 2 to the d points. It turns out, at least it's claimed in the miniature, that you cannot do any better. So we're just going to believe that. But yeah, it's kind of fascinating that by just changing the notion of distance, we've now upgraded the size of our set by quite a bit. Yeah. So give me a +1 if the example makes sense, and then we'll go on to the L1 distance. Yeah, let me know if you just want me to write out a couple of examples to make this clearer, but right. A typical vector that we're looking at would look something like this. We have also met these as like the characteristic vectors of subsets. So the point is, as long as you have two different subsets, they're going to lead to characteristic vectors that differ at least one point. So now if you look at the L infinity distance between these two, you're going to get 0, 0, 0, 0, 1, 0. That's the absolute difference between the coordinates, and you're taking the max of these. So that'll turn out to be 1 for any pair of vectors that you look at. So yeah, and there are the 2 to the d of these fellows, because like Saad was saying in the chat, for each coordinate you have a choice of 0 or 1. So yeah, okay. So I mean, I did think that this was fairly transparent, but let me know if any of this is confusing, or give me a +1 if you're good to move on. Yeah, good. Thank you. All right. Yeah, sorry to keep bothering you guys, but it's just good to know that we're on the same page, and that's super helpful. So yeah, thank you. All right. So the L1 distance is well, the coordinate-wise absolute differences just added up. Yeah, so that's the L1 distance. You could, yeah, I don't think we're looking at any other distances today. I suppose you could extend this to LP, but that's not something we're going to indulge in. So here, the question is, how many points can we have if you're working with the L1 distance? So you've seen that with the Euclidean distance, it's a strictly equilateral set can have only d+1 points. With L infinity, we can have 2 to the d points. Probably here we're looking at something in between. I don't know. So let's think in terms of examples first, because that tends to be a little bit easier to think about. So again, natural place to start may just be the basis vectors, for instance. So what about the basis vectors? Are they an equilateral set under this distance? Let's just take a moment to think about this. Notice that the previous example will not work because, well, you can probably, the example we had that worked well, infinity. Again, if we do the same thing, don't remember what I wrote out, but if you have two vectors that differ at exactly one coordinate, then you will still have a distance of 1. But let's say they differ at 2 coordinates, for instance, then for instance, this difference will turn out to be 2, right? Because the ones that match, they vanish, but the ones that are different, they add up. So this is in fact probably the L1 distance is probably going to be exactly the size of the symmetric difference of the set. So the Hamming distance is going to be the Hamming distance. So you don't have uniform Hamming distance across all possible vectors. It's going to be they're going to be all over the place. It's not even like two distances, or I suppose it's not even approximately equilateral, because the distances are going to range from 1 to if you just flip something around, right? So if you just flip all the bits, then the distance will be as large as d. So it's very far from being equilateral, yeah, in whatever sense. So yeah, the previous example doesn't work. So maybe we curtail our ambitions, and but still, I think it's mentioned in the miniature, and I should probably say it. The best known upper bound for the longest time was actually exponential. So for all you know, well, now not anymore because the upper bounds have come down, but for the longest time, I think people didn't, it was completely conceivable that you could have a collection of exponentially many points that are equilateral under L1. But But yeah, the example from before doesn't work, and that's clear. So let's, like I said, maybe let's just start small. And what about just the basis vectors? Can you maybe check if that's equilateral or not? And if it is equilateral, what's the common distance between any pair of basis vectors? So hopefully it's clear what these vectors are. So EI is the vector which has 1 in the ith coordinate. And yeah, so basis vectors have exactly 1, 1, and all the other coordinates is 0. And you're thinking of unit vectors, 1 being the distance. So, okay, yeah, so all the basis vectors are unit vectors, right? Krishna, you're saying that we could have more. That's probably true. And yeah, so I think we have a couple of proposals in the chat for the common distance, which look good. So Jayati is saying 1. It's close, but it's just you're going to have between two basis vectors, you're going to have two coordinates, two distinct coordinates that are 1, and everything else on all the other d minus 2 coordinates, it's going to be all zeros. So yeah, so basically those two coordinates are there. So EI and EJ basically will have the ith and the jth coordinate difference triggering a 1. So those two ones add up to give you 2, and everything else is 0. Right. So it'll add to 2 exactly. So Jagdish, Krishna, thank you. So that's perfect. So that's 2. And these are now D. But even with Euclidean distances, we got D plus 1. So can we ramp this up a little bit and squeeze in a few more vectors? So just extending from the basis vectors, maybe taking advantage of sign. Any suggestions? Maybe one thing that I'll say is suggestive is I want to double the size of this set. Can I do that for pretty much for free? And we're working in R, so we do have negative numbers at our disposal. Yeah, exactly.
I
So
think
yeah, sorry,
So
Ramesh.
no, the answer I think falls out if people know what the unit ball looks like in L1, then it
Right.
sort of becomes clear. Yeah.
Right. The unit ball in L1. Yeah, but okay, so by the
It's
unit
a
ball, I mean everything at
it's
a L1 distance of 1 from the origin, is that
Yeah. So at distance 1 from the origin,
correct?
and what you would get then is a diamond shape.
Mm-hmm.
Yeah. So then I think you'll have something like this. This is L1 thing. Whereas for the L infinity, the unit ball is like this. Okay. So
Right.
it's a appropriate cube. But here
Correct.
it's sort of a diamond. So
Yeah,
that
that makes
probably will tell you what to
sense.
do.
You get this idea of a reflection, I suppose. And also I think Jagdish has only sent this to me, but yeah, EI and minus EI is exactly what I was after. So we can add all the minus EIs to the mix, and notice that between EI and EJ, it's what we've already said. The distance is 2. Between minus EI and minus EJ, it's the same story. Between EI and minus EI, they're going to collide on the same coordinate, but you're going to get 1 minus minus 1. So that's going to add up to a 2. And between EI and minus EJ, or a minus EI, EJ, whatever, that's both the same thing really. But yeah, because you're counting the absolute differences, you're still going to get 2 1s from your 2 coordinates, which will add up to 2. Yeah. So is it clear that we have a collection of 2D points now, which are equilaterals under L1? And this is still it's not as massive an upgrade as before, but it's still substantially more than what we saw in what we can get with Euclidean distances. Yeah, okay, awesome. So that's as far as examples go, 2D points is what we have managed. In terms of upper bounds, apparently what was known, like I said, for a while was only an exponential upper bound. So there was I think this was, maybe there were other constructions, but I think the lower bounds were still linear. So between linear and exponential, there was still quite the gap. And apparently, at some point, there was some kind of a polynomial upper bound, and that's what we are going to look at today. And this was then further improved to d log d, but we still asymptotically, there's still a bit of a gap between the linear lower bound and the d log d upper bound. So I suppose that's still okay. So to be honest, I haven't actually checked on the state of the art, but I wouldn't be surprised if that's still a gap. So yeah, Vinay, you were saying?
Oh, nothing. Yeah, I continue. Yeah.
Oh, okay, all right. So yeah, this middle thing here is what we will try to look at a little bit today, again with appropriate black boxes and so on. However, according to the miniature, this improvement is apparently more of the same, but with tighter analysis, more careful choices, with the overall template of basically the roadmap of the proof is similar to what we are going to see. The techniques are similar. Okay, so what are we going to do? Here is the English version of the roadmap. So the L1 distance is apparently unpleasant. I don't know, it looks cute enough to me, but it's apparently not easy to work with, as probably if you actually work with it, you'll find out, which is not me. But anyway, so L1 is messy, but we already understand stuff about Euclidean distances, especially in terms of bounds for approximately equilateral sets. This is something that we already have from the proposition that we saw earlier. So if you could somehow map a hypothetical collection of an a set which is exactly equilateral in the L1 lens, if we could take such a set and lift it to a set of points, which would end up being approximately equilateral if you put your Euclidean glasses on, then we know that, depending on how the mapping works out and so forth, we know that this set cannot be too large, because we're assuming that the mapping preserves the distinctness of the points or whatever. That that you cannot have too many points in an approximately equilateral set under the Euclidean distance. So that's the idea. We want to find some means of transport from L1 to Euclidean that preserves distances, in the sense that if you are exactly equilateral in the L1 world, you're hopefully approximately equilateral in the Euclidean world in a meaningful way, meaningful enough that we can invoke our proposition from before, which was something about, what you can do within if all the points are like 1 plus or minus 1 over root n of each other, if that's the pairwise distance, then we know that there can be at most 2 times d plus 2 of them. So that's something that we are hoping to use if we can come up with this means of transportation. So the transportation is a black box. This is the approximate embedding lemma. Unlike the other one, the rank lemma is combine a few things and you work it out. This one, I have to admit that I don't even think I fully grasped it, but the tone of the proof was that, this is fairly straightforward. I think the precise phrase in the miniature is that we're going to take a simple-minded approach to the proof. And to be fair, he first works it out for d equals 1. And up to that point, things still seem okay. And then he said the rest of it kind of works out, which I think, maybe it was just that I didn't have enough time to walk up and down with what he was claiming. But yeah, if I were to trust the author, I will just pass on verbatim the idea that this has a simple-minded proof, and we can probably all work through it offline. But what are we trying to prove? Let's see. We are trying to say that you can basically go from this space here, 0, 1 to the d, to a much sort of a higher dimensional space, which gives us kind of what we want. That if you had so for us, we are going to start with a bunch of points which are exactly equilateral under the L1 norm, right? So in particular, let me just assume that, we have exact equilateral with unit distances. Then if you look at this inequality here, this looks a lot like what we had in the proposition, right? This looks like an approximately equilateral set of points in the RDQ space, right? So our function here is mapping points from 0, 1 to the D to RDQ. So our dimension also is exploded a bit. But what's happening in RDQ is that the collection of points we're looking at in RDQ as the images of F, if you were coming from a bunch of points that were exactly equilateral under the L1 norm, you will land in an approximately equilateral set. Where I should be careful. This is approximately equilateral according to our definition. If we can get these fellows here, this interval around 1 to actually be 1 over root n. N is the number of points. So here, this just basically gives us a means of transporting. You give me some collection of points, I will take you to a collection of points in a different space, which have some properties under the Euclidean distance. And if I were to read off what that property is, it will turn out, with some massaging, at least this is the plan of action, it will turn out that this set of points manifests as an approximately equilateral set, provided that we came from a collection of points that was exactly equilateral in the L1 space. So that's the claim. And like I said, the way the proof is written, it almost makes it sound like, it's a doable exercise. But like I said, the little bit that I tried parsing it, I think some of it is just like a little bit of careful calculation. And also maybe this is something that would be nice to actually think through as well. So I'm afraid this is something that I will not get into. We're going to assume that we have this embedding, but modulo this embedding, maybe for some of you it already feels awfully natural that, if you have this, then all the work is done for you, isn't it? But there's still probably a little bit of detail in actually using this a mechanism to prove exactly what we want. So it's mostly parameter substitution, but let's just go through it to make sure that we at least get what we want, assuming that we have this embedding lemma, okay? All right, so this is our precise claim. I don't know if I stated it in so many words before, but our claim is that you cannot have more than 100 d to the 4 points whose L1 distances are mutually exactly the same in RD, right? That's the claim. And so let's assume, so this is the template of the proof, right? We're going to say, well, suppose you give me a very large equilateral set, a very large set which is equilateral under the L1 norm, right? Then I'm going to use that very large set to go to a very large set that's approximately equilateral under the Euclidean norm. And now that we know cannot happen. So that's kind of, that's the plan. So we're going to prove this by contradiction. So let's say that somebody actually manufactures a very large equilateral set under the L1 norm, very large meaning at least 100 times d to the 4 points. This is, of course, something that has been reverse engineered to fit. So don't worry about the specific constant or the form of the polynomial so much. Apparently, this is where if you are willing to work harder and be a little more careful with your calculations, you can try to improve the bound. But this turns out to be convenient, as we will see. So in fact, we're going to replace the at least with exactly, which we can always do by dropping points. I don't even know that this is particularly important, but let's just assume that we're working with exactly these many points. Also, this is just, I think, more of a convenience thing, but also so that we can apply our transportation lemma, because the embedding thing takes points from 0, 1 to the D to RDQ. So as of now, we're dealing with points in RD. So we want to bring it inside this box here. So to do that, we just scale everything. I think that's yeah, so scaling is easy. I mean, you can make sure that whatever that common, so this is an exactly equilateral set. So imagine that you have the set on your iPad or something, you just pinch your screen to bring all the relative distances stay the same when you scale down. And then you move things around so that, one of your favorite points sits at the all halves location. This, combined with the fact that the intra distances are half, makes the entire point set come inside the envelope of the unit box in D dimensions. Is this fair? Is anything about this shady, or are we good? Let me know if we can move on. That's actually a general thing. I haven't asked it in a while. Hopefully the notation so far and the setup so far is fine. Didn't hear complaints. I'm hoping that it is, but give me a +1 if the starting point is okay. Awesome, thank you. All right, so okay, so we've brought everything within the fold of the unit box in RD, and again, this is more parameter pushing. We keep at the back of our mind that we are going to use our little embedding lemma with a particular value of q, which happens to be 40d cubed. That's not going to come to bite us until much later, but let's just have that at the back of our minds for whatever it's worth. So yeah, these are the points that we're going to push to RDQ. So D we already know because that's given by the lemma. That's where we're working. Q we needed to specify, so that's specified as some D cubed, some constant. So we're going to, those are the two numbers that we pick to plug in to this lemma here. And what the lemma is going to do for us is it's going to take every point in our assumed large equilateral set. It's going to take all of those points and dump them to various locations in RDQ, but with this nice guarantee. So how does that guarantee translate for us? Let's just take a look. So remember that all these L1 distances for us were half, right? Because that's how we scaled it down. So I can substitute a half there. And what else can we do? Let's multiply throughout by q so that we're looking at equal the Euclidean distances right there in the middle. So all I've done here is multiply throughout by q. So we have q by 2 plus minus 2d. That's the range of the Euclidean distances between any pair of points in this big dq space. And in the dq space now, I want to be able to see this in the form of 1 plus minus 1 over root n, because that's what my proposition back in the beginning looked like. So I'm going to scale things further just so that the format matches nicely. So so by dividing throughout when appropriate, so I want to get rid of the q by 2 and get a 1 there. So I want to kind of divide by 2 by q. So the points have to be scaled by a factor of root 2 by q for that to happen. So that's, again, a little more symbol pushing and calculation, but you can get this down to 1 plus minus 4d by q. So for me, my 4d by q is what I'm thinking of as 1 over root n. And that actually checks out in the sense that if you work through this, I think, let me see if that's also probably how q was chosen, because I know that n is 100 d to the 4. That's how many points we have. So we want q to be chosen so that this becomes 1 over root n. But we've already chosen q, and we just want to check that we've done that right. Okay, so so yeah, plug in q is 40d cubed. You'll end up with 10d squared for root n. So sure enough, n is 100d to the 4. So that's where the q is coming from. But on the other hand, we can also plug in our first proposition, which said that, well, look, this is an approximately equilateral set with respect to the Euclidean norm, and therefore you cannot pack in more than 2 times dimension plus too many points in here. And the dimension we're working with here is dq. So that becomes, what does that become? Q is 40d cubed. So that's 40d to the 4 plus 2. So that's 80d to the 4 plus 4. Certainly going to fall short of 100d to the 4. So that's the contradiction. A little bit of maybe like annoying symbol pushing here, but hopefully conceptually, if you believe the embedding lemma thing, hopefully conceptually the idea is clear. You're lifting to this larger space where your L1, your exactly equal L1 points magically become approximately equal Euclidean points, approximately equal points under the Euclidean norm. But there we can bring the force of the first proposition, where we know that you can't have too many of those. So you couldn't have had a large set to begin with. So that's about it. Yeah, so that's the proof of one of the main highlights here. And there were these two technical lemmas on the way that I completely gobbled up. And like I said, I promise the first one is like fun and easy to check. And the second one feels like it should be, but I couldn't bring myself to a point where I can say that confidently. But I think, I mean, I hope that that's something that we can all go back and convince ourselves of the truth of. Yeah, but with the symbol pushing and the parameter matching, if there's anything that looks fishy, or I mean, modulo typos, hopefully this made sense, but let me know if you have any questions. And maybe I should also say that, yeah, I'm pretty much done with what I wanted to say with respect to this miniature. So yeah, so any questions or comments, overall comments, all of that is welcome at this point. And we did finish a little bit ahead of 11. I think that was thanks to me not getting into some of the those two lemmas. But, you know, if that buys us a timely finish, maybe was a worthwhile trade-off. Okay, so I will really stop talking here and invite any comments, questions.
Yes, it looks like most of the linear algebra is in the, I think, how many? 5 left, is it? Or, 3,
There
4,
are
5 left, right? 5 left. I think maybe they are the places where there's heavier linear algebra possible.
I'm not even sure. Yeah. So, I mean, okay, but the last one, yes, there is some, you know, we've seen tensor products once, although I even hesitated to call them that. And there's this notion of a wedge product that comes up in the last one. And there are two stories to do with Shannon capacity, but that seems again more like stuff to do with the spectrum. One of them is called cutting cheaply with eigenvectors or eigenvalues, one of those things. So the three of these that are more about the spectrum and have more to do with eigenvalues and eigenvectors and eigenspaces and all of that business. And the last one is about the wedge product. And the penultimate one, which is 32, is yeah, that's another geometry themed miniature, but I haven't gone into it enough to know what the linear algebra components are. But I have a feeling that it's not much more complicated. I mean, yeah, it's still probably fairly elementary. So I think one of the things, I don't know if it was a conscious choice on the author's part, was to say that we're going to keep it elementary on the linear algebra side, but see how much we can push just the cleverness aspect of it to get non-trivial results in all of these other domains. It's geometry, combinatorics, graph theory, whatever, means set systems, etc. So yeah,
I think, I mean, the rank approximation that you had today, I think that probably will be a non-trivial lemma to take. Otherwise, I think all that we have been doing is, you know, somehow trying to argue that things are independent and so on.
correct.
Right? But I think this one is a nice theorem. I think
this one's definitely nice, and this one also, like I said, it involves making connections with the spectrum, so that comes up. And
so maybe whenever you start in Jan, maybe you should do the proof of this, simply because it's non-trivial. I think all other things I think we haven't done. I think the only thing I can remember is I think the rounding business, right? Where we actually rounded things to 0, 1 because we were taking this trajectory. We had a underdetermined system, and that allowed us to do things. That I think was a very nice lemma. See, eventually, if you're researching, what you want are lemmas, not theorems.
That's a fair point.
Lemmas are the tools that you'll use, likely use in your own work. Theorems are nice, but unless you work on that specific problem, it's not that much fun.
No, that's true. I mean, it's probably nice to the extent of being an advertisement for the lemmas, saying that, okay, these really have some muscle and, you know, you can do. But beyond that, this is absolutely true. You want to, the takeaways for most people are probably the tools from here. This I completely agree. And yeah, so I mean, again, I don't know. I mean, given that you pointed this out, let me just see if I can. Yeah, this is super lazy, but if anybody wants to go back and look at the miniature, it's really just these couple of paragraphs here where you're saying that, well, because you have a real symmetric matrix, you're looking at a real spectrum of eigenvalues and real numbers. So whatever the rank is, if it's R, then you have R non-zero things here. And so, like I said, the first thing you do is the Cauchy-Schwarz business on the lambda i's. And so you get something that suspiciously has like a similar form to what you want to show. But it turns out that it's actually really a useful starting point, because from here you use the fact that the sum of the eigenvalues is basically the sum of the diagonal entries. So you're already matching on the numerator. And then for the denominator, you have this relationship between the eigenvalues of A squared and the eigenvalues of A. And then again, the trace of A squared is just really this is again easy, because if you look at A times A and pick up everything on the diagonal, the ith diagonal entry is the ith row and the ith column multiplied by itself. So you basically see all the Aij squareds when you look at the trace of A squared. So everything really matches nicely, which is why I said it's kind of a cute proof combining facts that we all probably know, and it works out nicely. So I think it was a bit of a shame that I left it out in the first round. But this is just like, if anybody wanted to see what the proof looks like, it's eminently doable, I think. Yeah. Okay. So, all right, then I should let you continue, but I was just tempted to say a few words about this.
No. So I think it's a nice, simple proof. But I was just thinking, I don't know how much of lineage. I mean, you have to ask people who attended what they actually picked up, right, from this thing. So, for example, here there is something which says the sum of eigenvalues of A is equal to the trace, right? And so summation of the lambda is the same as adding up the diagonals and so on. Now, usual first course in linear algebra, I don't know, it depends on the course, but typically, if we all come from engineering colleges, they won't have done these things.
Okay. Yeah, that's a good
so, right? But I think people leaving the course, I think this course, I think probably should know a couple of more things in linear algebra than they did when they came in. That would be a nice thing, I think.
Yeah.
So I don't know, but you have to ask the people.
Absolutely. If anybody wants to volunteer information, that would be nice.
No. Each one should. I think if I were running this class, I would have made sure everyone would have spoken at least 5 times by now.
That's fair. I mean, I don't know if it's a function of me being shy, or if folks are joining in also shy. Probably not the best combination for that kind of interaction. So, but I think it would be. I mean, given that this is the last time that we're meeting, at least for now, ahead of the holiday season, this would be a nice time for everybody to chat.
I think.
Please, I think you should be able to unmute yourself. Please go ahead.
Hello. Am I audible?
Yes, you are very much.
So thanks a lot, ma'am. It has been great overall. Like Vanessa mentioned, we have learned small tricks in a way, and hopefully when something similar comes up in future, we'll be able to apply it, and that would be useful. It has been great to go through like different kinds of problems, and there have been like diverse techniques which were discussed. So that has been really nice.
So what was your favorite miniature?
I liked in the beginning there was that error codes one, and I think one more in between that was really nice. I forget. But these two I especially liked a lot.
What you've forgotten, you can't like. So that's the rule.
No.
It's just a memory thing.
I'm just missing it. Yeah.
That's the best if you think that that would trigger something. But yeah, error correcting codes was early on, like you said, it was miniature number 5. And then I don't know, we had the coin business, which I think Vinay was also mentioning. We had the person who wanted to avoid the shopping circle walking around in the yard. Spanning trees and error correcting codes, I think, took up 2 sessions each. Other than that,
Yeah, I think the spanning trees ones, right? Which went over 2 sessions, and yeah,
Yes.
that was the one. Yeah.
Okay, so you like the 2 really lengthy ones. Okay, I'm glad to hear that, because feeling a bit guilty about going over so badly on those, but yeah, I'm glad that you like them. Yeah.
So thanks a lot, and yeah, hopefully looking forward to the rest of the sessions in Jan next year.
Yeah, I'm looking forward to it too. Yeah, so yeah, thanks. You've been super regular, and thanks so much for joining in and making time for this. It's been wonderful. So yeah, I don't know if everyone here is pretty much a regular, so hopefully you're comfortable chatting and sharing any of your closing thoughts with us. Yeah. Okay, I think Manu has chosen to leave a comment in the chat. So thanks very much, Manu. I think it's an interesting quote.
Manu, you can unmute yourself.
Yeah, you please do, I think.
You can state it, yeah.
Hi, ma'am. Can you hear me?
Yes.
No, I attend some weekend classes sometimes. So one professor from TIFR, Vishal Vasan sir, he quoted this. So I really liked the quote and I remembered it after so many classes.
So Manu, what did you like? What miniature did you like?
Oh, I can't remember almost anything right now.
You have to remember only one.
I don't know.
And there's a very easy answer to that. You can actually say today's miniature and you're done.
Okay. But thank you so much, ma'am and sir. Thank you for all the classes. I really liked it.
It was really lovely of you to join, and I'm sure you have a pretty crazy schedule otherwise. So yeah, I appreciate you being around for the most part, and I do hope that you're feeling better. I know I got a message from Manu a couple of days ago and he wasn't around, so it was because wasn't particularly well at the time. I hope you are on your way to recovering, Manu. And
yes, I'm feeling little better. Thank you so much.
Okay, very good to hear. Thank you.
And thank you for all the other students also. It's very nice.
Oh yeah, totally. Yeah. So I'm going to second that, but once at the end, once maybe everyone's share their thoughts once. This purely by alphabetical order. Chinmay, do you want to say something? I know we've had a couple of chats of ours, but it would be really nice if you
Yeah. Hi, can you hear me?
Yes.
Hi. Yeah, I kind of joined halfway through, so I do plan on going through everything before Jan, before we meet again. Yeah, I really enjoyed all your lectures. And I think the problem statements are the most fun part, like just hearing you describe them and like, yeah. I think my favorite one was covering a cube minus 1 vertex. I think that was really cool. Being able to visualize that. Yeah, that's it. Thank you so much. I had a really good time.
Yeah, that's so lovely. And yeah, looking forward to hopefully coordinating in Jan again, and if you have a chance to look at any of the stuff by then.
Yeah, thank you.
Thank you. Yeah, between Jagdish, Krishna, Saad, any of you want to share your thoughts?
Just curious to know how you prepared. Did you used to prepare in the morning or day before?
Okay, that's a great question. I don't know if I should. We're still on the record, so I don't know how much I should confess to the fact that I'm a very last minute person. So a lot of this happens in the chaos, which is a few hours leading up to the. I think when I started out, I did have a buffer for a few days, coming in. So I think up to the error correcting codes, I kind of had some advanced prep going in, but as the days rolled along, I think I was very, paycheck to paycheck on the preparation. So often it was the same day, but it's, so I think you will probably see a lot of that lack of quality control showing in the slides, but I'm hoping that maybe one more round of this with some other excuse and things get cleaned up a bit. But
No, I think it is admirable. I mean, Jagdish knows me, so but I think it's impossible that if I were doing this course, I would probably be, in 10 or something of that sort by this time. Okay. I mean, there's no way I can read any of these miniatures in one day and then talk about it. So it's, I think, admirable that you've been able to do that. I think
that's extremely kind of you to say. I don't believe you one bit when you
No,
say
I just ask Jagdish. Jagdish, do you watch for me?
Yeah, I don't think he will be preparing slides and all.
Yeah, that is true. That apart. Okay. There's no way. I think I would have got stuck in some nitty-gritty detail somewhere, and I would probably spend a week thinking about it. It's the fact that you're able to do it on a daily basis, I think, is remarkable. I think it's not easy. I think.
Well, I don't know. Yeah, I mean, likewise. I mean, I don't think. Like I said, I mean, I don't think I would carry on through this if I didn't have this a really good group of people meeting up and spending time to look forward to. So I think I would have definitely lost steam as well if it wasn't for the fact that we were doing this together. So I think that's feelings more than mutual. So I think a lot of it has been, I think, the miniatures being kind of, I guess the way the book is structured makes it amenable to this format is one. And the other thing is, like I said, just also, I don't know. I think, of course, when I'm being there has made a huge difference because I'm like, I think very early on, I think he did say that he's, that I should probably not worry too much about all the slips and so on because he's going to be around, and having that help has been a huge sort of, it's just been has made the process of preparing, I think, fairly relaxed for me because I kind of knew that I have backups. So on the technical aspect, so that's been really nice, and of course all the added nuggets and information that we've had thanks to your being around has been super valuable. So that's been a huge help, and the rest of it is just, I think, me winging it through some of this chaos. I don't know. So but hopefully, I don't know. Hopefully somebody finds some of this useful, and then that would be nice to know.
Yeah. Thanks.
Yeah.
Krishna, you've not heard Krishna at all, I think.
Hi, I'm very happy to be part of this. So my math is very rusty. So my favorite miniature is the very first one, which I kind of understood, but all the others were a bit A-level for me. So part of them I thought I understood, but there is a lot of it I think that I still need to absorb. So that will take time. But the process has been very helpful for me just to pick up some interest in this subject and to see that there are so many different kind of problems where you can apply this. It felt very interesting.
Krishna, if may I ask, what do you do? Are you a student or a faculty, or I mean, working somewhere?
I'm working for the industry. I've been a student like more than like 25, 30 years back.
Oh.
Yeah.
Yes, I mean, I think, Krishna, I think the interaction that we've had with you throughout has been super helpful. So I think, thanks for being there for this pretty long sort of journey. I think that commitment between sort of a regular working schedule is just, it's just deeply appreciated. And I mean, hopefully as long as it was largely fun. And yeah, I agree that for me also the primary takeaways is that sometimes the statements are really surprising. The truths that we get to prove are unexpected. And sometimes the angle with which the linear algebra shows up as a tool for establishing those truths, sometimes that also is a fairly non-trivial element of surprise. So you get one or the other, often sometimes you get both. And yeah, so that's been one of my primary takeaways too. Like some of them feel you leaving very devoid of any intuition. It feels like it was totally crazy, but it still feels like, oh, this was good to know. So that's made it interesting for me as well. So yeah, thanks a ton for being there and for all the plus ones and and the questions and the discussions. It's been very nice having you.
Yeah, I think Krishna's plus ones is what probably propelled you into completing a lot of things.
Yeah, exactly.
So I, so that leaves with Saad.
Yeah. Yeah, I really love the lectures. It's a lot of fun to look at like different problems every day. I think it's hard to pick a favorite miniature. I think I liked the graph ones quite a bit, the packing bipartite graphs and the Peterson graph ones and the tiling rectangles one as well, and like matrix multiplication.
Okay, lots of them. Okay.
Yeah, I think I kind of relate to that as well. I think I'm partial to some of the graph ones too. But yeah, hard to pick a favorite. I would kind of agree with that sentiment overall. But yeah, I think I've always seen you around, so thanks a lot for joining and making time. It's really special having all of you really be so consistent in being a part of this. Like I said, I wouldn't have had the motivation if it wasn't for this fixture to look forward to. So thanks a ton for making it, Saad and everyone else. So I don't know if I don't know if Dad wants to say something. I don't know if he's around, but for those who don't know, that's I get a lot of. I think I've been getting some in-house tips, and Dad has been a bit of a volunteered helpline for me for when I get stuck with the math bits. So so Dad's been quiet through most of these meetings, but he's been around and very much a part of the process. So I don't know if you wanted to say something for Jen.
Yeah, all I can do is thank everybody for being around. It has been a very unusual experience for me because I really don't think in this way. I mean, this kind of combinatorial and whatever sort of way. Many remarks from Vinay particularly, I have been tempted to kind of say something or the other, but I mean, those sorts of things will take a while, and I'm more of a coffee room type of person. So having long chats without bound and so on and so forth. So that's one of the reasons I have kept quiet, because if I start saying something, it will sort of take away the focus from what is being. I mean, this is very concrete, whereas I'm quite the opposite, both in my thinking and doing things. But some of the very interesting comments from all of you, and the nature of these lectures has been very good. Hopefully, I have also learned a little bit of something. One of my colleagues, who is actually an expert, Bhaskar Bagchi, he used to. I mean, I sort of took a course more or less for a whole year in my early days at ISI Bangalore, and this reminded me a lot of that, and so I was very happy to be here. And of course, I must say that what my daughter says about in-house help, it has been minuscule. And she and I, if at all we start chatting about anything, very quickly diverge. So it hasn't been really of any help or any use. So I try to keep my mouth shut. Thank you very much, all of you.
Okay, all right, thanks. Thanks, Dad. But yes, so no, that's just yeah, no, it's really been so wonderful having having. I mean, it's quite a remarkable experience for me. The first time I've tried something like this, and it's been really cool that it's checked out in so many fronts, and I certainly learned a lot. And I've been a little afraid of linear algebra for the longest time. I think I'm a little less so now.
Yeah, for people who don't know, I mean, if I remember right, I think your father works in operator theory, I think.
He does. Yeah. So a lot
So
of
I was
that.
about to make a joke that he's quite the operator, but yeah. With that joke, I think.
I guess. Operator theory has that.
Operator,
yeah, right. Thanks.
No, I think, someday if I can graduate to the point where I can understand the jokes, at least I think I'll be fairly pleased with myself. But no, that apart, I think, so I think for, so I remember we had a linear algebra school at IITJN once, and I think I had tried to present some of these ideas there, but it was a bit left field because I think the school was, I think they were mostly working in, for example, in particular in finite dimensional spaces. So a lot of this was, I think, a bit of a culture shock to be working in finite dimensions, and there are all of these little things which are points of dissonance for people who are coming at it from a wholly different perspective. And I think, well, that's part of the charm, I suppose, that there are so many aspects to this. And I don't know, if you're probably a physicist or something, you probably have a whole other set of perspectives on some of the same tools. And it's like I said, I mean, I think for me, a goal has been to at least get to a point where I get some of the humor. And I think I'm laughing more when I'm browsing through Stack Exchange now, even at the linear algebra stuff. So I guess that's progress. But yeah, I think very special thanks to everybody for being here. But I think Vinay, basically, I don't know if without realizing it, you basically got co-opted into effectively co-teaching this. So really a lot of
it's a pleasure, I think. And maybe if everyone can unmute, I think we can thank Neil Dara, and then we can, okay, in unison. Few people are still not.
Two,
one. Thank you.
Thank you.
Yeah, all of you.
Thank you.
Yeah, or maybe clap or something. Yeah, maybe clapping is better. Yeah. All right.
Thank you very much, everyone. So on that
thank
note,
you.
for tonight. Thanks a ton, and hopefully see you back in January for a short reunion series. All right then. So good night, everyone. Thanks very much again.
Thank you.